Hello, Black Hat. We are very happy to be here and show to you our latest research regarding compression side channel attacks. Let us first introduce ourselves. I'm Eva, and here is Dionysis and Dimitris. We're researchers at the University of Athens in Greece, and this is a collaborative work with Professor Angelos Kiayas, who is chair in cybersecurity and privacy at the University of Edinburgh. As we assume that most of you already know that a breach broke HTTPS and RC4 back in 2013. People upgraded from strip ciphers to block ciphers to the EES and thought they were safe. But Rapture in 2016 attacked HTTPS with block ciphers. What we're going to show today is a generic defense for compressor side channel attacks. We propose that it's the best balance between compression and security regarding the other proposals. And we will launch today an open source implementation of our defense in many popular web frameworks. So what we'll talk about the next 1 hour is the history of compression side channel attacks and the attack vector. And then we will move to the CTX defense. We will define the origin, the secret, and the cross compression of the CTX defense, the permutation. We will discuss the CTX architecture, and then we will release our new tool, and we'll talk about future work. So in 2012, Crime was the first attack to successful attacks by side channel compression. It targeted HTTPS requests, mostly headers, to hijack sessions and steal cookies. And it took advantages of the characteristics of the deflate algorithm, which is the most popular compression algorithm of today. It hinted at attacking responses, although it didn't implement it. And after that, Crime was mitigated by disabling the compression at the TLS level. So no side channel compression attacks for HTTP requests were possible. Time 2013 exploited compression on HTTP requests. It exploited compression by measuring time transmission instead of size payload. And because of that, there was no need for man-in-the-middle ranges. Next was Breach, again 2013, exploited HTTP response body. The main secret was some secret tokens. It attacked stream ciphers, and it added some methods to bypass compression noise due to the compression attack, the Huffman pool. 2015, RC4 is considered insecure, and that's why most websites move from stream ciphers to block ciphers, and that's why now AES is the industry standard. Rapture 2016 exploits compression against HTTP responses. It attacks block ciphers, AES, and in order to achieve that, it performs statistical analysis and bypasses noise and length hiding. So even in the latest versions of TLS 1.3, Rapture is still possible. Rapture is a production code framework which automates the attack and makes the process much easier. And the last was presented in Black Hat USA 2016. It's Heist, which abuses the way responses are sent at the TLS level by changing the TCP window. And again, like Time, there was no need for a man-in-the-middle agent.
So let's go quickly through the attack methodology and how a compression attack works. I want to ask the audience, how many of you have seen any of the compression side channel attacks before, like Breach or Crime or Time, by a raise of hands? Okay, so most of you have seen this. I'll go through this real quick. So the idea here is that we have two plain texts test and test_rand. And if this compresses this and we compress this as well, then this will have a better compression ratio than this one, because here there's some sort of repetition. So if the plaintext is partially secret and partially controlled by an adversary, and it's taken through a compression function, then the adversary, by measuring the length on the network, they can tell if they actually hit the correct secret. So that's the basic idea of the this attack. And the two components, the two constituent components, are the reflection. This is a part of the plaintext controlled by the adversary, and then the secret is the part of the plaintext that is the target of the adversary. And so if we go to a diagram like this is the adversary. They're targeting a victim on the network, and then the victim hits an HTTPS website like Gmail, and the attacker makes the victim make several requests to Gmail, for example, by using JavaScript on some different website. Here, they're injecting some code to do that, and then they measure the TLS encrypted responses on the network and extract the length from that, because length is preserved across encryption. So that's the basic idea. And if we look at Gmail's response, for example, you see this exactly what's happening. There's a this is a search page of Gmail, and it includes two different things. Here's the CSRF token. If the adversary steals that, they can impersonate the victim. And then if the attacker puts on the URL some search query, this is reflected in the HTML like this. So if they search for this, it's reflected. And then if these compress together well, then the attacker knows that they get the correct secret. And they can do that letter by letter. So that's the basic idea. And this is already what Breach is doing and Rupture is doing time and heist.
Okay, so at this point, we will introduce our defense, which mitigates attacks that use this vector. So this is the CTX defense. And what this defense does is protect context by using a per-origin manner in order to separate secrets and avoid cross-compression between secrets from different origins. So this definition obviously introduces some notions that need to be explained. Firstly, what is an origin? So we say that an origin is the party that generated the secret. Now, this party can be either the web application or a user that uses this web service. And we will say that all secrets that were generated by the same origin will be compressed together, and we will allow cross-compression. Whereas two secrets that were generated from different origins will not be compressed together. So, for example, if we have an inbox, a Google inbox, we see that we have some mails, and the sender of the emails could be used as an origin. So the purple ones were generated by Eva, which is one origin, and the orange ones were generated by Dimitris, who is a different origin. So these origins generated some secrets, and these secrets, well, secrets in the HTTP response can be anything. Technically, any part of the response which is encrypted can be considered a secret. But in general, we'll say that a secret is any piece of information in the response that can be accessed only when the user is logged in. So this can either be some financial data, a CSRF token, some private messages or emails, or other sensitive data. So for example, in our previous example, we saw that Eva sent some emails, and the body of those emails can be considered a secret. Now, all bodies of all emails are secrets because they are sensitive data for the user of this service. But different secrets were generated by different origins. So the purple bodies of emails were generated by Dimitris and by Eva, sorry, and the orange ones were generated by Dimitris. So an orange email is a secret generated by a different origin than a purple email. And in that case, we say that secrets like emails that were generated from the same origin are allowed to compress together. So all emails that were generated by Eva will be compressed together, whereas emails that were sent from different people will not be compressed together. So we will not allow cross compression. And what is cross compression? Okay, let's say we have two elements in plain text. We have element A, we have element B, and if we allow cross compression, then the presence of A during compression will affect the compression of B. So, for example, if we are using the LZ77 algorithm for compression, and we have plain text A concatenated with B, where A is secret 1 and B is secret 2, then when using cross compression, LZ77 will actually use a pointer for the second secret string, and it will show to the first secret string. So the compression will be something like that. This is an example of a cross compression. If we don't allow cross compression, then both of these plain text A and B will be so LZ77 will not use a pointer. And how can we, in general, protect from our secrets from this side channel? There were proposed many solutions for solving this problem. And in previous papers, they proposed disabling compression altogether. Now, this method obviously solves the problem because compression is the side channel that allows this attack. However, the performance penalty that will come from disabling compression altogether is, in real world terms, unacceptable. So we can't actually disable compression. A second proposal would be to change the compression function and to change it in order to prevent cross compression between secrets and reflection or adversary generated data in general. But in theory, we're finding so far that all good compression functions are vulnerable, and we don't have a practical example of a compression function that actually prevents side channels like the one we saw before. So this also is so far not a good solution. A third solution could be to modify the web server and the compression module that runs on a web server in order to annotate different parts of the page and not compress these parts together. But this also has some problems because in this case, we have to both change the web server and the application level services. And also, this method actually makes it really kind of hard to achieve good compression rate. So it's in the middle ground, but it's not that easy to actually develop it. And a third solution would be to actually add some random data which prevent the attack from deducing easily what is a good compression and what is a bad compression. So when we run the different candidates in our attack, adding random padding would probably hide the fact that good candidates compress better than bad candidates. And this was actually implemented in TLS 1.3. However, in Rapture, it showed that this method is also susceptible to alignment, using alignment alphabet to result in blocks in block alignment in the block ciphers, or it is also susceptible to statistical analysis. So it is actually kind of a half measure. It doesn't solve the problem. It just pushes it to the future. Our proposal is actually to change the response plaintext. So this is in the middle ground, and we have implemented it in order to prevent these side channel attacks.
Okay, so CTX protects HTTPS responses, since we already said that due to the mitigation of crime, side channel compression attacks are no longer feasible So CTX is only for the responses. It runs at the application layer, so there is no need for modifications of the web standards or the web server, and is opt-in. As we will show from our experiments, it's the best balance between performance and security. We achieve full prevention of complete plaintext recovery just by a slight compression size increase and with just a small time performance overhead. So what we propose is a successful defense for all known compression attacks, such as all these that we mentioned before: time, crime, breach. So what the application developer has to do in order to include CTX defense to their application, they need to import two libraries, one for the server side for the specific web framework they use, and one for the client side. Then they need to select which portions of the context are considered sensitive secrets and define origin for its secret. Now, if we can divide our whole response in many origins, we could have one origin per secret, but this is the same as completely disabling compression, which is no good. And we could also have one origin for the whole plaintext, which would result in no CTX protection. So we need to define the origins for its secret. Here is an example. We have a for loop. This is a template, and we have a for loop for emails. And what we want to show is a table. It's the sender of the email and then the body. And what the developer has to do so as to CTX protect the sensitive part of the response, which is the email body, is that we use CTX protect tag, and we use email and email body and email sender. Email body is our secret, and email sender is our origin. After that, he has to include CTX permutations. This is a script tag with a JSON, which includes all the permutations for its origin. And the final one, the CTX.js, is the client. Now, if we didn't use CTX protection, this is the response that would travel through the network, and it would be encrypted, okay, but this is the response that the server would send. Now, if we use CTX protection, what an adversary would see is something like that. Instead of the CTX protect tag, we have this div here, which is a data CTX origin with an integer to define which origin this is. And then we have the secret, the email body, permuted. And now this is not easy. An adversary can distinguish and it can perform a side channel compression attack. Now let's talk about permutations. We need first to define the secret alphabet. This is we need to know all the characters that the secret may include. It could be ASCII, it could be UTF-8, or anything else. And then we perform a sender random permutation for the secret, for its origin. No, not for its secret, sorry, for its secret alphabet. And we use Fisher-Yates shuffle algorithm, which performs an unbiased permutation, meaning that each element has the same probability of being chosen. Then we permute the secrets using the origins permutation that we generated before. And then this HTTP response with the permuted secrets are TLS encrypted and traveled and transmitted through the network. Once on the user's browser, we apply inverse permutation and we decode the secret. Here is an example of how this happens. We have two origins, origin 1 and origin 2, and here are the permutations. Of course, there are more, but here is what we're going to need. And we have two secrets from origin 1, secret 1 and secret 2. As you can see, this is a permuted secret. We use the same permutation for the same origin. So secret and secret are the same. And okay, 1 and 2 are different because they have different permutations. And for the secret generated from origin 2, we have a completely different permutation because it's a different origin and a completely new permutation has been generated. The power of the bridge attack lies under the assumption that we can perform multiple requests to the target, and after that do some statistical analysis. What we've implemented is that per HTTP response we have new per origin permutations. So multiple requests are made, multiple and different permuted secrets are being transmitted through the network. Statistical analysis is no longer feasible.
Okay, so at this point, we have found that there's a problem. We have found that there are some attacks that use compression in order to bypass security. We have developed a defense that actually mitigates this problem. And we want to argue why this is a better solution than other proposed methods for mitigating these attacks. So we performed some experiment. In order to measure our defense we test the size overhead that is added to the response. So this is actually the kind of the bandwidth penalty when the server is sending the responses over the network, and the time performance, which translates to the server time, the time the server needs in order to apply CTX, and the time that the client needs in order to depermute the secrets that were sent over the network. So our web page is a 650 kilobyte HTML page. The uncompressed page is 650 kilobyte. This is fairly regular in real world systems like YouTube or Facebook. The timelines are about that size. We used 50 origins, so we assumed that in this page, the content was generated by 50 different people or channels, or even the application that generates CSRF tokens, for example. And we assume that 1% of this web page is actually a secret. So we distribute this 1% to the 50 origins equally. Now, 1% might seem a little low or might seem a little high. It is actually kind of higher than real-world systems use, because we found that, for example, a Facebook front page has like 0.5% secrets, and all other stuff in there are JS libraries or CSS libraries or static HTML code, which, well, is not a secret actually. So 1% might, in our example, might be a bit exaggerated for a Facebook timeline, for example, but with is actually a good rate to test our defense. And well, this 1% is equally distributed to origins, so we say that there is one secret position in the response per origin. Now, even if there were multiple positions, CTX allows cross compression. So even if we use like 2 or 3 secret positions, this text would actually be compressed together, so it doesn't make that much difference in considering our experiments. Okay, and we ran these experiments, and we found some kind of interesting results. So I will compare our defense with the other proposals. The first proposal was to disable compression altogether. And as I said at the beginning, this is actually kind of bad in performance terms. So if we disable compression in this web page with these characteristics, the size overhead will be 1.1000%. So the response that would be transmitted over the network would effectively be 12 times or so as the compressed one that is sent right now. So that obviously introduces a bandwidth problem, and also depending on the network that the user is using or of the server, this might result in actually a few seconds delay of loading time in the response. So I think that for a fairly big application that has not so many, like 1,000 clients, this is kind of bad. This is really bad. A second proposal that was actually used by Facebook in order to prevent exactly breach from stealing CSRF tokens from Facebook was masking secrets. And what this method does is it takes a secret and it generates a random string of the same size, and it applies an XOR of the mask, the randomly generated mask, and the secret. This is done for every response. So obviously, in every response, the transmitted secret will be different, and the attacker cannot use the statistical analysis to find the secret. But this method actually, what this practically does is disable compression, because if you mask a secret, then the data that will take the place of the secret will be practically random. So they will not compress well with the rest of the page. So in this case, you actually kind of disable compression for all secrets, and also double the size of those secrets, because each time you have to include both the mask secret and the mask in order to apply the demasking in the client. So in this case, if you practically disable compression for altogether for secrets, you have about 21% size overhead. So the page that will be sent over the network will be like 1.21 times the size it is right now. And well, that doesn't sound so bad. It might result in a few dozens of milliseconds delay for the network transmission or the web server to apply masking. Well, in some cases, if you're not so worried about performance, or if the secrets are that important, and you don't have any other solutions, well, it could be a solution. Yeah, you could probably use it. But what we propose, CTX, is actually allows for a better compression ratio. And that is because we allow compression of the secrets, and because the permutation is the same for all secrets, these will actually compress well, because the protected secret will have the same statistical similarities than the unprotected secret, although it will obviously be different because it is permuted. So in this case, our experiments showed that when using CTX for this same web page, the size overhead will be about 5%, which translates to approximately 7 kilobytes of data that will be sent over the network compared to what is applied right now. And this delay on the server side, in order to generate all the permutations, in order to mask all this, to permute, all the secrets, in order to create all the div tags and send it over the network and depermute it on the client and actually show the web page is a few milliseconds time, like 4 to 10 milliseconds. So this is pretty good. This performance penalty is, in general, could be considered acceptable even for large applications that have millions of clients. Because what this does is actually mitigate a serious problem with a very little performance penalty. And well, up to this point, we have seen that there are some different elements and some different parts of the defense that actually change how it runs. And these parts are the origins, they are how many secrets are in the web page. So if you have like 1% of the web page is secret compared to 90%, well, this obviously will affect the performance of CTX because there is much more things that need to be permuted. And also, if the total response is bigger, then CTX will also have a different type of performance penalties because CTX indeed adds some constant length of data. And that is, for example, the div tags or the JSON that has the permutations in it, or the actual CTX client script tag. So what we have found is that the more origins you use, the worse the performance of CTX will be. And that actually makes sense because if you use more origins, then secrets will be divided in more parts. So compression will be disabled for those parts. And the compression rate will go down. So performance will also go down. And well, deciding which origins you want to use is actually a good, it should actually be taken into serious consideration in order to avoid performance penalties that, well, could be avoided, for example. Also, if the total secrets in the web page are going up, then performance also goes down because the more secrets you have to mask, the more secrets you have to protect. So the bigger the permuted data in the response will be, the longer the permutation to be applied will be. So the server side and the client side that actually apply the permutation and the depermutation will take longer. So that actually makes sense. However, if there are more origins, more secrets per origin, then because CTX allows cross-compression, the performance will go up because the compression rate will be better. So secrets will be compressed together because they come from the same origin, and the length will be actually smaller because compression will be better. And finally, if the total response goes up, then the performance will also go up because as we, yeah, and that is kind of interesting actually because it's not so obvious at first why this happens. Why, when the total response is bigger, we have better CTX performance, and someone might consider if it could be possible that the bigger the response was, the more the secrets there were, and actually that would result in a worse performance. But the thing is that when you have a bigger response, then the actual byte size that will be included as an overhead in the compressed text that will be sent over the network is fairly the same. It's not that different. So for example, for a small page and for a fairly large page like Facebook, the overhead penalty in bytes will be from 7 to 10. It's not that much. However, the bigger the response of the less the impact this overhead will have on the actual performance. So for a large web page, these 7 or 8 or 9 kilobytes will be kind of hidden in the larger context of the response. So when you use a bigger response and when you have a bigger application, CTX actually is even better. So this is a diagram that shows exactly this. The x-axis is the response size. So we started from a 13 kilobyte web page. This is the not compressed HTML response of the web page. And we go all the way up to 650 kilobyte web responses like Facebook, like YouTube, like Twitter. And what we see is that the left y-axis is the percentage of overhead penalty that CTX adds. So for a really, really small web page, like 13 kilobytes, the penalty is kind of large. Yeah, the CTX will result in about 2.2% overhead in the gzip response. So it, if you have a website that sends back 10 or 20 kilobyte responses, CTX will kind of double or result in 2.5 times the gzip content that would be sent if you were not protected at all. But what this means is that actually the actual data that are sent, which are shown at the right y-axis, will be about a bit over 5 kilobytes. So because it is a small web page, 5 kilobytes make a significant difference. And yeah, it will actually be compared to what you had before, it will be much longer. But as you evolve your application, you add more stuff, you add more functions, you add more features, and the response grows larger, but you continue to use CTX, and CTX actually continues to add the same amount of response bytes. It goes from 5 kilobyte, and we see that for as the response page grows larger, the purple line actually goes down because this is the percentage of the CTX penalty, and the orange line will, well, it will stay the same at about some time, and then it will grow larger, but in a smoother way. So for example, for like a 500 kilobyte page, you will add 5.5 kilobytes of data, and this actually means that you kind of double the response, because yeah, you still have you still use CTX. It still disables compression up to a point, but if you use a web application that sends back like 600 kilobyte responses, the added data will be like 7 kilobyte. So the actual overhead in percentage terms will be about 10%, which is totally acceptable. It's because for in 600 kilobytes, well, 7 don't make that much difference at all. Okay, so these were actually the experiments that we run.
So I want to show you a little bit about how this works. CTX architecture. We'll go through the server and the client sides a little bit. So how does it work? What the server does is it goes through the tags that you have on your Django or whatever service that you're using, and it generates a new permutation for every origin. So if it sees a new origin, it will generate a new permutation. And notice that this is basically just a replacement cipher, like a Caesar cipher kind of thing, right? And then this permutation will be stored for each origin and applied to each secret. If two secrets share the same origin, then the same permutation will be applied to them. And notice that this happens every time a request hits the server. So the permutations are different every time, and this is why this works basically. And then at the end of the HTML body, in the way that you saw the HTML code, there's the tag that you saw with the permutations. This basically includes the data that allows the client to unpermute. So this is just a JSON data appended to it. So that's the service side part, and then the client side part just does exactly the opposite. So it looks for these specially crafted div tags, and then it goes through your DOM once the page is loaded, and also parses the JSON to find out what the permutations the servers, and then it applies the permutations in reverse on each secret so that the original data can be recovered. Okay, so today's a big moment for our team because we're making this software open source. It's actually right now open source on GitHub. We just made it public. You can go here to download it and install it. And you can also go to our website on ctxdefense.com to download it and install it. So today we're launching it for 3 web frameworks on the server side. One is Django, one is Flask, and one is Node.js. In Node.js, you can use a bunch of different templatings, like Jade, and it works well with the Express framework. This is MIT licensed, and we're also providing a client which is published on Bower, so you can install it on your websites right now and play with it. Yeah, and these, of course, the Python and Node frameworks are on PyPy and NPM. Everything is public. Okay. And then we're hoping that you will take our code and maybe implement it in different frameworks. We are the Python and JavaScript libraries that we have showed here. While we have provided specific implementations for Django and Flask and Express, we have also provided generic libraries for the cryptographic part. So you can just reuse these and build your own for your own framework or your custom web application, like Ruby on Rails. And then this implementation works for limited encodings, so limited alphabets. We are hoping you can contribute with different encodings because otherwise it's not very usable. So yeah, if we only support ASCII and UTF-8, maybe some languages will not work well. And then if you want to also go on our GitHub, one other thing that we want is to support client-side frameworks like React, so that this protection can also apply on JSON RESTful endpoints. That would be good. Okay, so the key takeaways is HTTPS plus gzip is still broken. Even if you use TLS 1.3, this is still attackable. We showed you also some examples of interesting adversarial cases where the reflection is not very clear. For example, there's one adversary-controlled email body and one victim-controlled email body, and the adversary can use that as a reflection, which is quite counterintuitive. And then CTX is a solution to this. So we invite you to start using it, start reporting bugs, and show us if it's good or not. Tell us what you think. So that's it from us, and we'll be happy to take your questions.
Are there any questions? Oh, yeah. Sure.
So the HTTP headers are typically not compressed. If you use the latest version of TLS, the request is not compressed at all, and the response is not compressed. And then the body of the HTTP is compressed, but that doesn't include the header. The header defines the compression method. So you're safe on that. Any other questions before lunch? Okay, so let's go back to the email case. That's a good question. So I say here, the problem with breach is that if the adversary is sending the victim emails, say that Dimitris is the adversary here, and he's sending me some emails, and these are specially crafted reflections, and he wants to steal whatever Eva has sent me on this other email. That's kind of the attack model there. If Dimitris is able to find out one word from this email, these two will compress together. So if we use the same permutation for these two, then these will still compress together. That's kind of the point. But if we use a different permutation here and a different permutation there, then these will not compress together. But the emails from the same origin will compress together to achieve better performance. So that's the reason we have to have separate origins. Okay, any other questions? All right, thank you very much.